Hey guys, myself P. Ramsachari from CSC section. In this video, we will learn about simplifying context-free grammars. Topics: Introduction, context-free grammar, conclusion. Introduction. A context-free grammar (CFG) is a formal grammar which is used to generate all possible patterns of strings in a given formal language. It is also defined as four tuples. G is equals to VTPS. As we know that G is a grammar and T is the final set of terminal symbols, V is the finite set of non-terminal symbols, and P is the set of production rules, which is used for replacing non-terminal symbols in a string with other terminals. S is the start symbol used to derive the string. Example, the grammar brackets P is equals to A tends to A. These are the three examples. The definition of context-free grammars allows us to develop a wide range of grammars. Most of the time, some of the productions of CFGs are not useful and not redundant. This happens because the definition of CFG does not restrict us from main these redundant productions. By simplifying CFGs, we remove all these redundant productions from a grammar while keeping the transferred grammar equivalent to the original grammar. Two grammars are called equivalent if they are produced the same language. Simplifying CFG is necessary to later convert them into normal forms. Types of redundant functions and productions and producer of removing them are mentioned below. Here there are three steps to simplify the context of a grammar. First step, useless productions. The productions that never take part in derivation of any string are called useless or useless productions. Similarly, a variable that never take part in the derivation of string is called useless variable. For example, S string A, B, S. This is an example, and in this example above, production C is useful because the variable C will never occur in the derivation of any string. The other productions are written in such a way that variable C can never reach it from the starting variable S. Production is also useful because there is no way it will ever terminate. If it never terminates, then it never produces string. Hence, the production can be take part in a derivation. To remove useless productions, we first find all the values which will never lead to terminal string such as variable B. We then remove all the productions in which all variables B occurs. So the modified grammar becomes this. When we try to identify all the variables that can never be reached from the starting variable such as variable C, then we can remove all the productions in which variable C occurs. The grammar below is now free of useless productions. The second step is lambda productions. The productions of type A tends to lambda are called lambda productions, also called as lambda productions or null productions. These productions can only be removed from those grammars that do not generate lambda. It is possible grammar to continue null productions and it not produce an empty string. To remove null productions, we first have to find all the nullable values. A variable A is called as nullable if lambda is can be derived from B. For all the productions of type A is nullable variable. For all the productions of type B, A1, A2, AN, where all AIs are nullable variables. B is also a nullable variable. After finding all the nullable variables, we can now start to construct the null production tree grammar. For all the productions in the original grammar, we add the original productions as well as all the combinations of the productions that can be formed by replacing the nullable variables in the production by lambda. If all the variables on the RHS of the productions are nullable, then we do not add a tends to lambda to the new grammar. An example will make the point clear. Consider the following grammar as shown in the below. Let's first find all the nullable variables. Variables B and C are clearly nullable because they contain lambda on the RHS of their production. Variable A is also nullable because into both variables on the right hand side are also nullable. Similarly, variable S is also nullable, so variables S, A, B, and C are nullable variables. Let's create the new grammar. We start with the first production, add the first production as it is. Then we create all the possible combinations that can be performed by replacing nullable variables with lambda. Therefore, now becomes we apply the same rule to line, but we do not add a tends to lambda even though it is also possible combination. We remove all the productions of type V tends to lambda. The new grammar now becomes below. And third is unit productions. And step 3 is unit productions. The productions of type A tends to B are called as unit productions. To create a unit production tree grammar, GVF from the original grammar, GV follow the procedure mentioned below. First, add all the non-unit productions of G in GVF. Then for each variable A in grammar G, find all the variables B such that A star tends to be for all variables like A and B, where B none of the x1 to x10 are single variables because we only added non-unit productions in G. We, we only added non-unit productions in G. And the resultant grammar is unit production tree. Example is given below. Let's add all the non-unit productions of GF. Now it becomes, now we find all the variables that satisfy X, A, B, C, and D. We add because B exists in GF. Now becomes, for B tends to A, we add B tends to B because A tends to B exists in GF. The new grammar now becomes S tends to A tends to B slash A, B tends to A slash B. We follow the same steps for S tends to B and finally get the following grammar. Now remove B tends to B since it does not occur in the production S. Then following grammar becomes S tends to A slash B slash A slash A tends to B slash A. Conclusion. To remove all kind of productions mentioned above, first remove null production, then the unit productions, and finally remove the useless production. Following this order is very important to get the correct results. Hence, this is all about the simplifying of the context-free grammar. Thank you.